Hello everyone, welcome to my poster. First, let me give you some background. Deep neural networks are typically compressed before deployment on embedded platforms because they are very computational intensive for such platforms. However, the assumed hardware resources at design time may not be available at runtime. Model compression is a trade-off between accuracy and latency, so we don't want to over-compress the model. In the figure, model A and E are compressed at design time to just meet the required latency target while keeping the accuracy as high as possible. You can see in the scenario of BCD and FHG, when the frequency changes at the runtime or when the model is sharing hardware resources with other applications, then the result of design time compression are no longer valid. One solution to solve this problem is dynamic neural networks, which can be executed partially to trade off accuracy for latency, power, and energy reduction. In the figure here, we have one dynamic neural network backbone with 4 different subnetwork configurations. For example, 25% model only uses 25% of the model parameters for inference. And the 100% model is the full model. The 100% model is more accurate but also slower. At the runtime, different subnetworks can be switched and executed for different amount of available hardware resources. Here we have some results for accuracy, latency, and energy consumption trade-offs. In the figure, subnetworks are shown in different color and computing elements are shown in different symbols, such as A7 and A15 heterogeneous CPUs on Audrey X23 and the CPU GPU on Jetson Nano. The frequency scaling is shown in different points. Let me give you an example of how it works. On Audrey X23, if we have a 100 millijoule energy target and a 400 millisecond execution time target, then the best operating point is point A because it has the highest accuracy under the execution time constraint and has the lowest energy consumption. And if the constraint changes to 200 millijoule and 200 milliseconds, then point B will be the new best operating point. Now, what about power? Here we plot the power consumption trade-off from both Audrey X23 and Jetson Nano on the same figure. As you can see here, the power of a single core CPU scales with frequency but does not scale with the dynamic neural network. This is because the computation intensity does not change on CPU with smaller subnetworks. On GPU, we have a different story. You can see that the power consumption scales with frequency as well as the dynamic neural network. This is because smaller subnetworks use less GPU cores for inference. This is very important because we have a new method to reduce the power consumption at the runtime. In summary, we think studying the trade-off opportunities in machine learning model and combining them with the traditional frequency and voltage scaling is the key to deliver better performance trade-offs. In this way, the system can consistently meet the performance target when the hardware resources are dynamically changing at the runtime. If you want to know more about dynamic neural networks, please check out our CVPR workshop paper. This is the end of my talk. Happy to answer any questions. Thank you.